Okay, so this lesson, it is our lesson 15. It corresponds to chapters 22 and 23 in the textbook. And I titled it Buffers, even though really it's only chapter 23 that's about buffer systems, because chapter 22 is all about weak acids. But in order to understand buffers, you have to understand weak acids. Okay? All right, so first question we're going to deal with. How do we determine the strength of an acid? How do we determine the strength of an acid? So you'll remember last week we talked about that we've got strong acids and we've got weak acids. And it's one thing to describe materials that way. That's called a qualitative description. But we want numbers, right? This is chemistry. This is a hard science. We want numbers. Okay? And so you'll remember that weak acids donate fewer of their hydrogen ions than strong acids do. Right? This is something we talked about last week. Do you remember this? Talking about this last week. Weak acids donate few of their hydrogen ions. And what this means is this. If this is an acid, which it is, and if this is a strong acid, which it also is, what we're not saying by it donates all of its hydrogen ions is that it's going to do this. We are not saying this. Okay? We are not saying that when we say that a strong acid donates all of its hydrogen ions. Okay? We're not saying this, and you're like, Dr. Engel, how can we not be saying that? That's what all of its hydrogen ion means. What we're saying is this, that if we have 50 molecules of this acid, that a strong acid generates 50 hydrogen ions and 50 molecules of HSO4 minus. Okay? Do you see that minus there? I kind of ran out of space and had to smash them together. Can you see it in the back row? Okay. It's not ideal. I wrote too big. I'm sorry. So what we're saying is a strong acid, if it donates all of its hydrogen ions, every single molecule you have in that solution is going to lose its hydrogen ion. Okay? Notice it didn't lose both, but every single one of them lost its hydrogen ion. That's what we mean when we say a strong acid donates all of its hydrogen ions. We do not mean this. Okay? We do not mean that if we've got this acid here that it's going to donate both. It's only going to donate one, typically. We can find situations in which it might be both, but it certainly wouldn't be all 50 molecules are going to donate both. Okay? Even though it's a strong acid. But all 50 of them are going to donate their one hydrogen ion. Okay? Does that make sense? That's an important point of clarification that I didn't do a good job of explaining last week. I also didn't do a good job of explaining on Monday. I talked to them a little bit about it, but then afterwards I was like, wow, I didn't do a good job explaining this. Need to make sure I do when I record the lecture. Okay, and we're like, okay, cool, but we're still just talking about qualitatively, right? This donates all, this donates some. Let's put some hard numbers on it, shall we? And here's how we determine the strength of an acid quantitatively. Here's how we determine the strength of an acid quantitatively. What we do is this. We calculate what's called the Ka. We calculate what's called the Ka. May I erase this that's on the board? You know, it would help if I just got into the habit of starting over here. I'd end up with a lot of space to write. Okay, so we've got this number, Ka. We saw a number last week that was K something. Do you remember what it was? KW. And it was a constant, right? This is also a constant. This right here, Ka, is called the dissociation. Oh, is it two S's? I think it is. Dissociation constant. And so when you see Ka, this is a constant number for every particular acid. It's a constant. And dissociation constant. What does this word dissociate mean? It is a shortening of the word disassociate. What does it mean to associate with someone? It means you interact with them, right? If you disassociate or you dissociate from someone, you stop interacting with it. It's a beautiful name for this constant because it's basically a representation of how likely is that acid to dissociate from its hydrogen ion. Right? Okay, so it's how likely is this acid to dissociate from its hydrogen ion. If it's a strong acid, the Ka, we don't even need to measure Ka because it's always going to dissociate from its hydrogen ion. If it's a strong acid, right? We said strong acids donate all of their hydrogen ions. Doesn't matter how many of them you have, they're going to donate all of them. Every molecule is going to donate its hydrogen ion. Not an individual molecule is going to donate every hydrogen it has, but every molecule will donate its one hydrogen ion. But weaker acids, those that aren't strong, they are going to have different degrees of strength, different degrees of dissociating from their hydrogen ion or giving up their hydrogen ion. And the more likely they are to give up their hydrogen ion, the stronger they're going to be. Does that make sense? Okay. So in order to do this, we need to know the reaction. In order to calculate the dissociation constant, we need to know the reaction. We need to be able to take an acid and know exactly what we're going to get when we put that acid into water. Okay? So we need to be able to come up with the reaction. Now, in order to do this, we need to know what the conjugate base is. And the conjugate base is a very fancy term for what's left over when the acid dissociates. So in order to predict the reaction, we need to know the conjugate base. We need to know what's left over when the acid dissociates, when it donates its hydrogen ion. Is the green okay to see back in the back row? I don't know how green looks. Let me take a little walk. See how the green looks from the back. Oh, that's nice. That looks good. That's sharp. That's a good color. Okay, so we had this, right? I just showed you a reaction where we had this, and I said a strong acid donating all of its hydrogen ions does not mean that this acid is going to get rid of both its hydrogen ions. Instead, what it means is this. Okay, that's what it means. And so this right here is our conjugate base. This right here is our conjugate base. It is what's left over when the acid dissociates. When the acid donates its hydrogen ion. This is what's left over. This is the conjugate base. Okay? So in order to come up with this reaction, we need to know about that conjugate base, and we need to be able to come up with what it is. We also need to know that water, that we're going to put these acids into water, and water is going to take on the extra hydrogen ions. So when this acid donates its hydrogen ion, water absorbs it. It takes that hydrogen ion on to form H3O. All right? That's something you need to keep in mind. Because when we take these acids, and we're talking about that acids donate hydrogen ions, we're talking about when the acids are in water, when waters are solvent. And so, you're not evacuating the building, are you? Okay. All right. And so, water's going to take on those extra hydrogen ions. Okay, and that's something you need to know and you need to keep in the forefront of your mind. Okay? So, how do we determine the strength of an acid? The best way to answer this question is to just write two letters, Ka. How do we determine the strength of an acid? Ka. Ka. That's how we determine the strength of an acid. Shall we? But before that, the key term, if you could look up conjugate base, and then also Ka. So when you look up Ka, make sure you put Ka acid, because if you just look up Ka, I'm pretty sure that the Greek letter Ka starts with Ka, and it might tell you that, and that's of no use to you. Yeah.
I couldn't find conjugate base. I just found it though.
Oh, okay. So I want you to look up conjugate base and Ka as far as acids are concerned. All right? Well, now let's do this. So let's take an acid, put it into water, predict the reaction, and then to figure out or calculate the Ka, and then from there, calculate the pKa. The pKa. All right. So first acid, H3PO4 in water. H3PO4 in water. Okay, so this reaction, H3PO4 in water is going to produce, now it is an acid, which should make sense because this whole chapter we're talking about right now is weak acids. So this is an acid, and what do acids do? They donate their hydrogen ions. And do they donate every hydrogen ion in the molecule? No, if they're a strong acid, every molecule donates its hydrogen ion. But so what this is going to do, when H3PO4, it reacts with water, it's going to form one molecule of H3O+. And why is that positively charged?
It took on a positively charged.
Right, it took on a positively charged hydrogen ion, and before it was water with a neutral charge. And when you're neutral and you take on one positive charge, you become positively charged. It's like if you have no money and somebody hands you $1, you now have $1. Right? It's not like starting with where you're in the hole, right? You owe somebody $1, somebody hands you $1, you don't really have $1. You have one in your hand, but it belongs to someone else, right? You're back to neutral. Okay, and then what's left over? So it's going to give up one of its hydrogens to this water molecule, and then what's going to be left over is our conjugate base, which now is H2PO4. It was H3PO4, but now it's given up one of its hydrogen ions to water to form H3O. And what is the charge on this? -1. How do you know? Because, yeah, this took on a positive charge, meaning that this positive charge had to leave here, but before, we're not showing any charge, and if you lose one positive and you were at 0, now you're at negative, right? And so what would we call this? The conjugate base. The conjugate base. And if you wanted to know what you would call it, it would be dihydrogen phosphate. But anyways, that's neither here nor there. We'll talk about how to name things in another day, and you'll love it. Okay? Any questions about this reaction? Okay, let's do another one. So now we've got H2CO3 in water. H2CO3 in water. H2CO3 in water. Okay? So we're going to react this with water. And if this is a chapter on weak acids, it tells us that this is what? This is a chapter on weak acids, so what is H2O3?
Weak acid.
It's a weak acid. And what do acids do? They give up their hydrogen ions. They actually take on electrons, but that's a different thing of what acids do. But they give up a hydrogen ion. This is going to give a hydrogen ion to water to make H3O positive, and then we're going to be left with our conjugate base. And if this gives up one hydrogen ion, what's left? HCO3 with a negative charge. And why the negative charge? Yeah, it started neutral, it gave away one positive charge, now it's negative, right? It started with nothing, it gave away a positive charge, and now it's in the negative, okay? Or if you started with nothing, you lent somebody $1 you didn't really have, now you're in the hole, right? You're in the hole. Or you spent $1 you didn't really have, that's even better. You're in the hole, okay? And what would this be? The conjugate base. The conjugate base, and specifically this is called bicarbonate, like sodium bicarbonate, which is the active ingredient in baking soda. Okay, just to kind of put this. And this right here, this is the most common buffer system in our bodies. Since we're talking about buffers, this one right here is the most common buffer system in our bodies. But we'll get to that in a couple of weeks. All right, last one. HF in water. HF in water. HF in water. And so HF in water, if this is in a chapter on weak acids, what does it tell us about HF? It is a weak acid, and what do acids do? They give up their hydrogen ions to water to give us H3O plus and fluorine with a negative charge. This is fluoride, the ionic form of fluorine.
Is it missing L from the HF? Or does it not have an L?
Oh, it doesn't have an L. Sorry, I got excited and added an L there. It's just F. F minus. Maybe I didn't want to write that because it sounds harsh. I don't know. I got excited. Okay, fluoride. And so all three of these are weak acids, meaning not all of these are going to get converted into the conjugate base, right? Some of them are going to remain as HF. Not all of these are going to get converted into bicarbonate. Some of them are going to remain as H2CO3. Not all of these are going to get converted into dihydrogen phosphate because it's a weak acid. Some of them are going to stay as H3PO4. And the question is, how much? And now that we have the reaction, we can calculate the Ka. We can calculate the Ka. Shall we? We shall. We shall. So what is the Ka? And I'll go ahead and put these all back up on the slide. What is the Ka? What is the Ka? Okay. We're in a good spot. May I erase this? I'm going to leave those on the board because I need the reaction to stay up. Because I told you in order to calculate the Ka, we need to know the reaction. And so here's how Ka works. Ka is equal to the concentration of our two products divided by the concentration of one of our reactants. So for this reaction here, so I'll number these 1, 2, and 3. And then that way we can 1, 2, and 3 up here. Okay, keep track of everything. So the Ka for this here is going to be the concentration of H3O plus times the concentration of H2PO4 minus divided by the concentration of H3PO4. And so the Ka is equal to the concentration of products that we make multiplied together, the concentrations multiplied together, divided by the concentration of what we started with. Now, we could calculate this as long as we could do this reaction in the lab and figure out these concentrations. And guess what we're going to do for our lab 6? We're going to take some of these weak acids, we're going to dissociate them, and we're going to calculate some of these ourselves. But I will tell you that the dissociation constant for this acid, H3PO4, let me get it right, is 7.52 times 10 to the minus 3. 7.52 times 10 to the minus 3. And you're like, that's so cool. That is so cool. Now, if it's a strong acid, why can't we calculate Ka? Anyone notice this? Y'all are now experienced chemists. You should be able to look at this and determine why we can't actually calculate Ka for a strong acid. Is there going to be any of this left over for a strong acid?
Nope.
No, it's going to, 100% of it's going to dissociate, which would make its concentration what? 0. Can you divide by 0?
No.
You cannot. So you can't calculate Ka for strong acids. They completely dissociate. But you can for any acid that's not a strong acid. If it's not a strong acid, it's a weak acid, no matter how close it is to being a strong acid. Even if there's just a little bit left, like in this one, just a little bit left, it's still a weak acid. All right, now Ka. How would we do Ka for H2CO3? What would our concentrations on top be for that reaction? H3O plus still. That's one of our products. Times the concentration of what? HCO3 minus. Divided by what?
H2CO3.
Our concentration of H2CO3. And that's how we would calculate Ka for this acid, H2CO3. And the Ka, and remember these are constants, 4.3 times 10 to the minus 7. 4.3 times 10 to the minus 7. Is that Ka smaller or larger than the Ka for H3PO4? It's smaller, right? Because we've got an exponent that's more negative, meaning you're putting more zeros after the decimal point. So which one of these is a stronger acid? H3PO4 or H2CO3? H3PO4. The higher your Ka value, the stronger the acid. And now we have a way where it's not just like, oh yeah, this donates more of its hydrogens than this does. But we actually have a number. We have a number to assign to it. And we have a number that we could calculate experimentally. We could do that. And we're going to do it. We're going to do it. You're going to love it. And it's very simple to actually do it. Can you think of how we could do this experimentally? Now that you all are, again, you are budding chemists, you are developing and becoming more and more chemically minded, how could you do this experimentally? Could we figure out a way to start with a specific amount of this? Sure, we just measure how much we want of it, right? We start off with a very set amount of H3PO4. We know exactly how much there is. We put it into water, pure water, and if we measure the pH, and we know pH tells us our hydrogen ion concentration, it tells us how much of this we've made, right? Yes? So we put in a very specific amount of this. It tells us how much of this we've made, which tells us how much of this we've made, because if you make, say, 5.0 times 10 to the minus 5 moles of this, you have to make the exact same amount of this, right? Because for every one hydrogen you use to make H3O, you had to pull one hydrogen off of our acid, and it generates this conjugate base. So by measuring the pH, we'll know this, we'll know this, and if we know this, we know how much of that is left over. Because we know how much we started with. And you're like, cool, we can go in and we can test all of these numbers and see if it's what we get in the lab. Do we get these dissociation constants? You're excited about it, aren't you?
Yeah.
I mean, they're weak acids, but that doesn't mean, so like the pH of this acid is still really low, even though it's a weak acid. It doesn't completely dissociate, but its pH is still really low. Meaning it's still dangerous to work with, which creates a little bit of excitement in the lab, right? No? Kind of. Okay. All right, number 3. Now the Ka for HF. And how would we calculate our Ka? So we're going to start with H3O, the concentration of H3O plus, multiplied by what?
The
Concentration of F minus, divided by concentration of HF. Okay, the concentration of HF. And it is 7.2 times 10 to the minus 4. So the Ka for HF is 7.2 times 10 to the minus 4. Yeah, Joe.
When you say concentration, you just mean molarity?
Uh-huh. Yes. Yes, I do. Yep, molarity is one way to measure concentration, and it's the way we do most often. There are other ways to measure concentration, but they're rarer. Yes, the molarity. Yep, it's a good question. All right, and we're like, cool, now we know the Ka. We have a way to quantify the strength of an acid. But how do we attach this back to the pH? How do we attach this back to the pH? Okay? And so here's how we do. We take the pKa. So we can attach this back to pH by determining the pKa. Okay, by determining the pKa. So let's write the 1, 2, and 3 again. pKa for 1, pKa for 2, and pKa for 3. Now what is P again that we saw last week? It's the negative logarithm of the concentration of whatever follows, right? So pH is the negative logarithm of hydrogen. pOH was the negative logarithm of hydroxide, right? Do you remember that from last week? So what is pKa then?
The
Negative logarithm of Ka. So this is going to be the negative logarithm of 7.52 times 10 to the minus 3. Right? You okay with that? What would this one be? What would number 2 be?
Negative logarithm of 4.3 times 10 to the negative 7.
Negative logarithm of 4.3 times 10 to the minus 7. And then this one would be the negative logarithm of 7.2 times 10 to the minus 4. All right? And these, unfortunately, are not like the problems we did last week, where it was 1.0 times 10 to the minus something. And you could just change the sign of the exponent because these are not 1.0. These all have complex numbers. So now we actually have to put this in. We've got to take our calculator and we've got to do negative logarithm of 7.52 times 10 to the minus 3. Which gives us a pKa of 2.1 for this H2PO4. And again, we're doing this to relate it back to pH. That's a pretty low pH. If this is at its dissociation constant, this is a pretty low pH. Okay, pH of about 2, similar to lemon juice. Now the pH of any strong acid is going to be 0. Okay, if any of our strong acids that completely dissociate, the pH will be 0. But you can't calculate Ka for a strong acid because you can't divide by 0. But you could rest assured that if you calculated the hydrogen ion concentration, it'll be 0. Okay, well, what about this one? Negative logarithm of 4.3 times 10 to the minus 7. And we get a pH of, or a pKa, which, if it's at its dissociation constant, would be a pH of 6.4. That's pretty close to neutral, right? Neutral pH is 7. And that's why this right here is such a great way to buffer our pH, and why this is the most common buffer system that you can find. Because when it's at its dissociation constant, it's really close to neutral pH. It does a good job of actually keeping our systems close to pH. All right, and then finally, negative logarithm of 7.2 times 10 to the minus 4. And we get 3.1. So if it is at its dissociation constant, that is, you've allowed the reaction to take place the way it should, that the pH is going to be 3.1. Okay. Any questions about this? And so now we've taken it, we've oh wow. Oh, yeah. Got to pull all those out. So we've recircled it around and gone back and related it to pH. Okay. Any questions there? So now we have ways of quantifying weak acids. We can quantify them based on their Ka, their dissociation constant, how good are they at getting rid of that hydrogen ion, and we can quantify them based on what their pH would be if they're allowed to fully dissociate the way they want. Okay? Sound good? Does it make sense? Is it all right? All right. So last thing, an introduction to buffers. What is a buffer system? What is a buffer system? And again, as you work through, you'll be able to do all of the questions on lesson 22. You'll be able to do all of the questions on lesson 22. You won't be able to do them all on lesson 23 unless you read through the text and you learn it on your own, but we'll come back to it in a couple of weeks. All right? So simply put, a buffer system is a weak acid with its conjugate base. A buffer system is a weak acid with its conjugate base.
Is that the answer?
Yeah, you can say, yeah, absolutely. That could work as the answer as well. So if you want to write over on the right, see my first point, or you just rewrite it a second time over on the right. But yes, a buffer system is a weak acid with its conjugate base. And you're like, cool, but what does that actually mean? Because what does a buffer mean? If you are acting as a buffer between two people feuding, what does that mean?
It's kind of a cushion.
Yeah, a cushion. Yeah, absolutely. Have you heard that before? Somebody describing themselves as a buffer between two people that are in some kind of a feud. We used it a lot when we were talking about World War II with neutral countries. that were a buffer between the two feuding parties? Maybe?
Like when you have a car and there's a seat with like the 3 seats next to each other and there's one person stuck in the middle to make sure the other 2 don't fight.
Yeah, absolutely. Although all 3 of my kids fight, so whichever one ends up in the middle, it doesn't act as a buffer between the other 2. Yeah. I never realized why my fighting with my siblings bothered my parents so much until I became an adult. You're just like, man, does literally everything have to be a fight? Like one of them will be in the back seat and it's like, the sun's in my eyes. And then another one will be like, no, the sun's in my eyes. No, the sun's in my, and they're fighting. And I'm like, no, the sun is in both of your eyes. It's an equal opportunity blinder, you know? But they got to be the best. Okay, so here's how it actually works. So when you have a buffer system set up, you've got the weak acid and you have its conjugate base. If the pH of the system moves towards the acidic end, that is, you start to pump a lot of extra hydrogen ions into it, the conjugate base will gobble up some of those hydrogen ions and shift it back towards the basic end. So again, if you've got this system set up where you have both the weak acid and its conjugate base, if you start pumping in extra hydrogen ions because let's say this is in your blood and you ate something that was particularly acidic, and so it starts to create some extra hydrogen ions that can get into your bloodstream. This buffer system in your bloodstream, the conjugate base of H2CO3, for instance, which is bicarbonate, will take on some of those extra hydrogen ions and keep the pH from dropping down lower. Shift it back up as you start to trap some of those hydrogen ions. Because if you trap them, they're not free in solution, lowering the pH. They're trapped. Is that beautiful? Like, man, this is so wonderful. And then also with buffer systems, if the pH moves towards the basic end, that is, you start to put a lot of hydroxide ions into solution, the weak acid will donate more of its hydrogen ions to balance that out. And when you take a hydrogen ion and add it to a hydroxide ion, it forms water. We saw that last week. So when the pH moves towards the basic end, the weak acid will donate more of its hydrogen ions than what it would typically do to balance that out. And are you getting the sense that these buffer systems are a great design to maintain pH? Because they are. They're a great system. These buffer systems work to balance and maintain the pH of our solution. The pH drops, our conjugate base will take on more hydrogen ions. If the pH rises, the weak acid will donate more hydrogen ions. And it's all in an effort to balance and maintain the pH. And that's why throughout all of the tissues, all of the fluids in our bodies, you have these buffer systems to buffer against big fluctuations in pH. Because as you could probably imagine, having the pH of your blood drop below a certain level would probably not be that great, right? You start to expose things to an acid, bad things can happen. Which we'll see a little bit of the next time we do a lab in 2 weeks. We'll expose something to an acid just so you can get appreciation that even though it's not a strong acid, it can still do some things. All right. Any questions or concerns? Did you all get the worksheet for this week? And I told you, you'll be able to answer all the questions from lesson 22. You will not be able to answer all the questions from lesson 23. And I'm going to remind you that's because in 2 weeks from now, we will finish our conversation about lesson 23 in the same week that we do our lab 6. Okay? All right. Well, Have a wonderful conclusion to your day.